Okay, now you're good.
Are we good?
Yeah, you're good.
Okay, so like I said, how far back do I have to go? I'm sorry.
All the way.
No, it's fine, just pick it up here.
Oh, okay. So that sigma pi gold digold complexes are where you have the one gold compound bound to the alkyne in a sigma fashion, and then another gold compound comes in and coordinates in a pi fashion. And they say that this happens in the reaction flask when they're just sitting around. And that the reason why it sticks around is because your gold acetylide bond is stronger than gold in another random alkyne just coming in and trying to displace it, so it doesn't break apart. So this paper is trying to figure out if these digold complexes are in fact a reactive intermediate. So what they say is you get your, well, this is slightly different, but you have your substrate, and then you get this, your digold intermediate, then you get a geminal digold intermediate, so where they're both sigma oriented, and then it forms this reactive intermediate where they're kind of all in this transition state, and then the golds fall off, and then you get your product. So they're saying that this digold is critical to forming your and then others are saying that it's a dead end, that once you get this, it can't re-enter your catalytic cycle, and it just sits around and does nothing. So to answer this question, they formed their gold library. So they formed a bunch of, or not a bunch, but like they formed like 2 acetylide complexes, so just the sigma oriented, and then they did digold, oh wait, sorry, that's 3 of them, sigma complexes, and then you have your digold complexes where and the way they compare them is essentially you have an alkyne, and then they use n-butyllithium to deprotonate it, and then react it with this IPR gold chloride, and then once that's in the flask, and this is at like -50 degrees, and then your gold 1 catalyst, so that A, B, or C earlier, comes in and just coordinates in a pi fashion. And they confirmed all these structures via X-ray diffraction. So the studies they did, so with the acetylides, they basically just put these with the substrate, see if they reacted. So they reflux the gold acetylides in chloroform, deuterated chloroform at 60 degrees for up to 2 hours, and they didn't get any product. And after a while, they started to get some decomp. And the only way they got this reaction to work is if they added a strong Bronsted acid, which would cleave that acetylide bond. So basically, they came to the conclusion that gold acetylides are not a reactive ingredient. And so then they looked at their digold complexes, and so they found that normal with the antimony counterion, they didn't get much reactivity. So they used the Barth counterion, which they assume is going to encourage dissociation, which is why it works. So they're saying that instead of this digold, like when you have that reactive gold 1 complex by itself is when you get your reactivity. And then they did a bunch of theoretical studies with all these digold complexes to show that they're more stable, and that's the reason why they don't react. So that's why they're dead, because when they coordinate that sigma pi fashion, they don't fall apart. And so, in conclusion, the monogold pi coordinate species are your reactive intermediate, and Barth for either one is a better counterion. So they did it for the literature, and then they also went back to the previous ones, and they saw that Barth helped the reaction wall, and they said it assisted in aryl transport. I think that's it.
Bravo. All right, go back, maybe forward. Yeah, right there. So they're saying that these are the reactive intermediates?
No, they're saying they're not.
But they're saying also that the digolds aren't?
Yeah, so they were making sure that these weren't, like, so they were trying to find out which actually is. So
So I guess which ones are the reactive intermediates?
Do I have a picture? Okay, these. I'm pointing. These. So what? Well, this one is a nitrogen, and none of those actually have the alkyne. But essentially, these are reactive because their ligands fall off. So they're saying that that you just have the gold one by itself. So there's like previous literature, there was like maybe that after this ligand falls off, then it coordinates to your alkyne, and then the other gold comes in, and that's how that reaction happens. But they're just saying, so once you get this gold one by itself, high coordination, and then it does the reaction.
Okay.
So can you do a couple slides forward? Right there. So that number 17 right there, it looked kind of similar to one I had on one of my papers. So did they find that basically if you have that weak ion interaction, that even with that it would not end up undergoing this, like the catalytic cycle, because
They didn't talk much
it's
about
only
their
got
catalytic
like
cycle.
one open active site for anything to come in and bind.
Yeah,
so does that
that's
really
what
prevent it
the-
from doing anything.
The little things are for to crowd it out, but I don't know. They didn't really talk about that. They just said whether or not it actually did the reaction. They didn't go into much mechanistic stuff besides whether digolds worked or not.
So are they saying 16 is the reactive intermediate or reactive?
No. So none of the digolds are. So they had to synthesize those by themselves because normally it was proposed it happens in the reaction class, so they made a bunch of them, and then they looked at their reactivity by themselves, and none of them worked until you added like counterions to help them break apart, essentially. So none of the digolds are the reactive. So the reactive intermediate is so I guess it's not shown, but it's just, so you see A, B, and C, you get these gold complexes, and then once this ligand falls off, you just have this gold one counts by itself, and then that coordinates with your alkynes, and that gives you your reaction.
But it doesn't get stuck there.
It doesn't get stuck with what?
Well, like once that ligand falls off, or
Yeah.
that counterion falls off, you end up with your ligand attached. But like,
Yeah, so they're saying it's just the two together, so just your gold one callus and just one ligand. There's no second gold one that comes in.
you want to say it stops right after
Yeah,
that.
okay. Well, it does reaction begin.
Yeah, it does the reaction. Then you get that, and you're just done.
Go back to all your structures again. So the rationale I was thinking was that they were using these large, bulky ass groups to be able to make it so that some of them only form the single gold complex, and then some of them they'd be smaller and they could get two of them on there. But it doesn't really seem to be the case, because 15 and 16, that's the exact same phosphine ligand, right? And the CHT acronym is the same cyclohexyl whatever thing that's sitting right there.
Yeah, the triangle. Yeah.
So 15 would be
Seems
a
strange to me.
reactive species.
This is all, none of this works. That's
Yeah,
what-
none of it works. I'm just wondering, like, I'm just interested
Yeah.
in why I guess they were using.
I think because that's what they always used. Because they most of it's recycled from other papers. So like,
Yeah. So
I don't know if they made any conscious decision to use that or not.
It's strange. I was just also thinking that it's going to be so bulky around the gold that it's interesting that it catalyzes these cyclization reactions, just because the substrate itself is going to be so damn bulky. So to have that, have a bunch of isopropyls and T-butyls all over the place seems strange, but I don't know. What's our electron count on most of these guys?
We should have all been prepared for
It's
these
gold.
questions.
It's gold at 9 right now, or is it at 10? Like When it's not
When it's what? When it's neutral, it has 11.
11? Oh, okay. So that's, oh, no. Yeah, okay.
Maybe it's like slightly paramagnetic.
Yeah, there's seems like some strange electron counts here.
So these are both like -1s, right? So that will come out, or well, with the triple bond, that would be like 6 or something like
Yeah, that'd be 6, and then it's gonna be 8 of 3, so.
Well, but you're doing just a single sigma to
So
that
you'd be
carbon. The
17.
triple
Yeah,
bonds
yeah,
to the other carbon.
Yeah.
You'd be at 17, and then if that other carbon over there, so wouldn't that be 18?
that.
For 17, that would be like an 18 one.
17, I think. For this one, at least.
That's what
How are we getting 17?
Oh,
Is
jeez.
it 16 then?
Well, how are you counting the?
Well, so I was like, this is just 1 - 1. So that's 2 electrons. And then this is a -1, but 6 electrons. So then this.
Well, that would still only be 2 electrons.
Oh, it's
on the
only 2
right.
electrons?
Yeah, because that triple bond is between the carbons, so it's going to
Oh,
be.
okay.
Oh,
It's
so
gonna
just
be-
actually 1 carbon.
So-
Yeah, it's just going to be a
It's
2 electron negative 1
Well,
donor.
13.
Yeah, right? Weird.
Yeah, it's crazy.
I hate those things.
Somebody's lying.
I'd be like, and there's a hydrogen.
So
wonder it didn't
my
work.
other thought, and I'd have to do more reading, I suppose. My other thought is maybe they're using these bulky ass ligands to
Don't
try
know.
to prevent decomposition pathways of various sorts, since it is kind of a low odd electron count.
Can I ask you a question? What's BARF?
Barf. So barf is a borate anion. So it's boron's neutral and it has 3 things. So now it has 4 things. Carries a negative charge. The barf part is it has 4 aromatic groups, and all of the hydrogens have been replaced with fluorides. So that's why they call it barf. And it's really good because it spreads that negative charge out across all of those aromatic rings that have those fluoride electron withdrawing groups.
That sounds crazy.
So yeah, it makes it so that it doesn't really want to coordinate to anything, even if it is negatively charged.
Why did they do the F at the top?
That's just to indicate that that's the substitution of all the hydrogens.
That's weird.
If they don't have the F, then it's just the normal aromatic rings with all the H's still in there. But yeah, barf is just the the word you hear people throw around whenever they give presentations with it. And they're like, oh, we use barf as a counter ion. Everybody just nods their head. And I'm like, yes, we know what that is. Okay, nice work. Go.